Okay, so we are the first two authors of this paper, me and Elvis, and we will present tonight. Sorry, we will present our participation to the CLEF HIPE evaluation campaign. I will start by making a short introduction about the tasks and the challenges. There is a risk that everything has been said before, but maybe there is someone new in the room and he doesn't know about them. I will continue with the name entity recognition and classification task with the models, the experiments, and the results that we had, and Elvis will continue afterwards with the models, the experiments, and the results for entity linking, and we will finalize with some conclusions. For this evaluation campaign, there were proposed two tasks. One, the identification and classification of name entities. As in this example, Michael Jordan should be recognized as a person, and then the identification and disambiguation of these name entities by linking them to knowledge bases. As for example, Michael Jordan is either a footballer or a basketball player, etc. But this main challenge in this evaluation campaign consisted in the characteristic of the data sets, because they consisted in historical documents. Therefore, this implies the existence of an OCR that transcribes the text, and then there's an error propagation towards the modern algorithms that are used for text processing tasks or for these specific tasks. Not only that the documents can be damaged or have low quality, but also there can exist some spelling or grammatical variations due to different periods in time. Another challenge would be the segmentation format, because for example, this is common for this type of documents. It's either at line level or article level, and line level might be a bit too short for algorithms to grasp. The informative features, as for example, in the figure on the right, there are some lines where only one letter has been recognized and wrongly from the next line. And also article level might be a bit too large context for these algorithms. Finally, this datasets proposed by this evaluation campaign consisted in 3 languages, English, French, and German. And this can also affect some models because either due to the low resourced languages or lack of NLP tools for processing them. The global architecture that we propose consists in a first pre-processing step, and then 3 models for the name entity recognition and classification, and then the model for entity linking for the 3 languages. For the name entity recognition and classification, there were proposed 2 subtasks, one for the identification and classification of the entities in coarser grained entities as in person, location, organization, and the second one for the detection of finer grained entities, as for example, nested entities or components belonging to an entity mention, such as a person's function, title, honorifics, etc. We start by pre-processing the data set, and this is mainly the decision that we took for the segmentation. So we segment the text at sentence level, and for reconstructing the original text, including the hyphenated words, we use a tool called FreeLink. For the name entity recognition and classification model, we propose a model that consists in a pre-trained language model, and then we add a stack of transformer layers on top. And we finalize with a commonly used CLEF. For English and German, we chose to use the BERT model, which is a bidirectional stack of transformer encoders that consists in 2 tasks. One, the masked language model, where the model learns how to predict a random word in a context, and then there's next sentence prediction, where the model learns how to predict the next sentence. In the figure on the right, there's a transformer architecture, which that first was proposed in 2017, and it consists in an encoder and a decoder. Firstly, it was proposed for a translation task. Therefore, it needed a decoder because the inputs were a sentence and the output was also a sentence, the translated sentence. But in the case of BERT, BERT only has transformer encoders because it doesn't need a decoder. And this the same model that we use to stack the layers on top of the language models. Finally, we approach the name entity recognition in a multitask manner, which means that we train and predict the coarse and the fine entities at the same time. For German and for English, as I said before, we chose the BERT model. For German, we chose a model that was trained on historical documents. And we have two main runs. The first run was BERT and the CLEF layer. The second run was also BERT, and we add two transformer layers on top and finalize with the CLEF. For French, we chose the Camembert large model because it has the highest results for French text processing tasks. Camembert actually is a Roberta language model, which actually is also a BERT model, but with a different training strategy. It has a dynamic masking for the first task, and it does not have the next sentence prediction task. We have two similar runs for this. For French, Camembert alone with a CLEF and Camembert alone with two transformer layers and the CLEF. For English, since there was no training data provided, firstly, we chose to use only BERT alone and the CLEF. And we have two approaches for English. The first two runs, we chose to use a modern English dataset, which is Cornell 2003 dataset, and we chose BERT large because it has the best results for English BERT models. And the last run, we chose to train this model on the German and French datasets, and we used a multilingual BERT, as in a type of almost zero-shot transfer learning. From the results, we can notice that the run 2 has the highest results for German and French, which implies that the model based on the pre-trained and fine-tuned model language model and the stack of transformers on top have the best performance, while for English, we can notice that the run that we use the German and French datasets to train, at least for microphasy, the results are higher than the other ones. And the results are lower when trained on modern English datasets. We afterwards performed an analysis of these results in order to understand what was happening. We noticed that the model with a pre-trained and fine-tuned language model and a stack of transformers can actually increase the ability of the architecture to better model long-range context. We also noticed that BERT alone has unbalanced a type of unbalanced attention to misspelled and corrupted words, when actually the most informative words are these words that contain errors. And therefore, BERT alone creates many more spurious cases. Finally, for French, we noticed that for around 56% of the different values of the Levenshtein distance that was provided by the organizers after the competition has finished, the models that had the stack of transformers on top had relatively more better predictions. A deeper analysis of all these results and why did we choose two transformers, or what are the parameters and what happened to the predictions and etc. will be presented in a paper in the Cornell conference this year. Just a simple example in German, where BERT in the second part, the lower part of the image predicts some random persons and locations, which is extremely spurious results, and the BERT model with the transformers on top can actually manage not to predict such type of wrong predictions. Thank you very much, and now I will leave you with Elvis that will continue with entity linking, and I hope that he'll be able to share his screen also.
Thank you, Emma. Wait a minute. I think you should stop your screen first. Okay, thanks. So can you see my screen? Yes. Yes. So thank you. For entity link, you have here an overview of our model. So in the left side, we have all the resources that you have used to disambiguate dimensions. So we extract the Wikipedia dump in each language of the campaign, so French, English, and German. With this dump, we extract pages and links to train our entity embeddings and also to compute the prior probability distribution of an entity being related to a mention. So in the middle, you have here all the input data, so the historical documents in German, French, and English that they are analyzed and processed by OCR corrections of these mentions to remove some noise generated by the OCR engine. So all this information is processed by the entity link model, that's in this case the CLEF, that take the OCR corrections, also the entity embeddings, also the prior distribution to provide a global disambiguation, but also we analyze the most fractal entities that are related to a mention. We combine all these predictions, and finally we use a filter that requests some data from DBpedia and Wikidata to provide our output. So analyzing each part of this model more smoothly, we have here in the first part the build and resource. So we analyze the Wikipedia and the Wikidata, model Wikidata to make the link in between the Wikipedia pages with the Wikidata ID. So for each language, we compute the probability entity map. So in this case, we extract the Wikipedia dump for French, for English, and German. And for each one, we take here the titles, the ideas, but also the disambiguation page and the redirection page. And you calculate how an entity E is related to a mention M based on the number of times that this mention referred to the entity. This part is really important because you provide all the candidate entities for each mention. Based on this probability, you have an idea of which entities you have to analyze and disambiguate in the entity disambiguation model. So then to calculate our entity embeddings, we use the Ghanaian-Huffman model that we're gonna project these entities in the same dimensional space of the word embeddings. To do that, we analyze two conditional probabilities. The positive one for approach the embeddings of co-occurring odds with the embeddings of the entity that you are training, and the negative one to put away all this representation of our entity. So in this case, if you have an entity like Microsoft, we have a similar representation for computers or for Bill Gates, for example. And for our entity disambiguation model, used here the model of Colzer that use a BLSTM model where they analyze the word and character embeddings to provide a representation of a mention that after we analyze this representation with the prior distribution of this entity of this mention with all the candidate entities. Also, the similarity between this mention and all the candidates that you have obtained from the prior distribution, and also the attention mechanisms to analyze this mention with all the other words in the sentence. So this analysis will provide a local score, and after with the analyzing all the other mentions, you provide a global disambiguation. And finally, in the end of our system, we have a filter that in this case, you extract the information from DBpedia to get more information about some name entity types. For example, when you have a mention that is from of the type location, you can get the information of the DBO location and DBO settlement to get the information about the country or the continent, or for example, the amount of people that live in this place. For the type per person, you can get the date of birth and the year. And for example, remove some candidates that have the year of birth that is much recent than the newspaper publication year. So you're not talking about the same person in this case. And finally, for the new output, if you have the case here, for example, Paris, France, we know that it is a location. So if you're having the candidate like location, person, location, I'll filter you change this list, you put location, location, new, and move the person candidate to the end. And if you have, for example, all the candidates are the type person, but I'll mention this type location, so that you provide only the new output. In this case, you can avoid several noise, or for example, candidates from different times, or they're not correct to this to this mention. So for our experiment, we use here the pre-trained multilingual multi-word embeds that project a word of different languages in the same dimensional space. In this case, for example, we have gato and cat with similar representations. For training our model, we provide a model for each language, where German and French model were trained in the HIPE training datasets. For English, we use the IDA dataset to train our model. And for minimize the OCR problems, we analyze several variations of these mentions. For example, the concatenation of the mention if there are like 2 words or 3 words, the log case, no punctuation, and the Levestein distance to get more candidates for a mention. So for both tasks, we provide 3 runs. The first run for the only entity link task, we use the output of the culture model and the top 5 candidates, here the most frequent candidates. For the run 2, we have only the most frequent candidates, and the run 3, we have the culture and the 10 most frequent candidates. It's interesting to remember here that the filter it's after this process. So the filter you have to remove or change the order of these predictions. And for the end-to-end task, for the run 1, we have dimensions that were recognized by the NERC run 1 and the entity linking run 1. For run 2, we have the second configuration for NERC and the first configuration for entity linking. And for run 3, we have 2 different configurations for some languages. For example, for here, German, French, we use the run 1 of name entity recognition to recognize dimensions, and the run 2 for disambiguating them. And for the English, we use the run 3 of name entity recognition and the run 1 of the entity linking. So if analyze here in the first case, we don't have any information about the type and the boundaries of dimensions. So you can see that run 3 achieved the best F1 scores for English and French for the literal analysis, while the run 1 achieved the best results for the metonymic analysis. So in this case, the filter here works quite different because it depends of the output of the name entity recognition. So if the difference you can see with the difference of the performance of the each run of name entity recognition systems. For the second case, we have here the ground truth provided by the organizers about the type of dimensions and the boundaries. You can see that the results are quite similar in this case, with the run 1 achieving the best results for both analyses, and only for run 3 achieving the best results for the literal analysis for German. So to summarize the results, you can see here for the when we have the knowledge about the type and the boundaries, we got quite similar results for our language, with run 1 being slightly superior for the others runs. Another interesting thing here is the filter that reduce the performance of the entity link system for English and French. if you come back here, the run 1 and the run 3 are quite similar. The only difference is the amount of candidates that you use it. For example, run 1, we use only the 5 most frequent entities, while the run 3 uses the 10 more frequent. This difference occasionates some increment of noise, because when you use the Wikidata for the run 3, we don't remove the name of this migration page, and also few 10 more candidates can also change the new output for our system. So more details will be available with the paper that's coming soon in the ICADL conference, that you analyze all the effects of this, for example, using Levi-Stein distance, also using all the kind of filters, will be affect the result of our system. So to conclude, we provide 2 models here, one for name entity recognition and classification, that is a stack transformed based model with a fine-tuned BERT that they're trained in the HIPE training data set, and we use a transfer learning process to train our English model. If for the entity linking, we use the neural-based model combined with the filtering process that uses the information from Wikipedia, Wikidata, and the Wikipedia that enable us to make a deep analysis of the entities and help our system to disambiguate historical documents. Thank you for your attention, and feel free to ask if you have any questions.